Hello everyone, this is Aytekin. In this video, I will talk about my course project and project literature survey. The topic is real-time semantic segmentation for autonomous driving. I have selected one of the earliest studies on this area, Efficient Convolutional Neural Network for Real-Time Semantic Segmentation by Eduardo Romero. In the paper, the main idea is to find an efficient and reliable architecture which can work on at edge devices. The CNN in the paper builds up an efficient redesign of convolutional blocks with residual connections. Residual connections suppose a breakthrough because they avoid the degradation problem that is present in the architectures with a large amount of stacked layers. This has allowed very deep networks with hundreds of layers to achieve outstanding classification performances. In the paper, an architecture proposed as a wider architecture as opposed to a deeper that makes an extremely efficient use of its minimized amount of layers to achieve accurate segmentation in real time. You can find detailed information in my project proposal. After this brief explanation about the paper, let's continue with the outline of the presentation. The outline of the presentation is as shown. Let's continue with the introduction. Semantic segmentation is a fundamental problem in computer vision and an intermediate goal towards solving higher level tasks such as scene understanding or sensorimeter control. The goal of semantic segmentation is to assign each pixel in the image a label from a predefined set of categories. The task is illustrated in the figure using an example from the CitySpace dataset. Segmentation of images into semantic regions that are typically found in street scenes, such as cars, pedestrian, or roads, allows for a comprehensive understanding of the surrounding, which is essential to autonomous navigation. The task is difficult due to the complexity of the scene, complicated object boundaries, illumination, small objects, and the large size of the label space. For methods, as we discussed, the goal of semantic segmentation is to assign semantically meaningful class label to each pixel of an image. Traditionally, the problem was posed as maximum posteriori inference in a conditional random field, abbreviated as a map in a CRF, defined over pixels or superpixels. Hierarchical and long-range connectivity as well as higher-order potentials defined on image regions have been exploited to compensate for limitation of CRFs with local connections and to model long-range interactions with the image. A traditional method example from the figure, which is published in CVPR 2004, the problem was posed as map in a CRF defined over pixels. In this example, instead of pixels, the problem is posed as map in a CRF defined over superpixels, published in CVPR 2006. CRF models which model pairwise potentials between all pairs of pixels in the image. While previous methods using fully connected CRFs could only be applied to smaller image regions due to the computational and memory complexity of these algorithms, with some studies, fully connected CRF models at pixel level is deployed. An alternative to inferencing graphical models for the task of semantic segmentation is presented. They train a sequence of inference models in a hierarchical procedure that captures context over larger image regions. This allows them to bypass the difficulties of training structured predictions model when exact inference is intractable and yields a very efficient and accurate scene labeling algorithm. While most previous approaches rely on very simple features such as color, edge, and texture information, the paper observed that more powerful features have the potential to significantly boost the performance. They propose an approach based on a novel feature type called texture layout filter that exploits the textural appearance of objects, its layout as well as textural context. They combine texture layout filters with lower-level image features in a CRF to obtain pixel-level segmentation. The success of deep convolutional neural networks for image classification and object detection has sparked interest in leveraging their potential for solving pixels-level tasks, in particular semantic segmentation. The fully convolutional neural network illustrated in the figure is one of the earliest works which applies CNNs to the image segmentation problem. Modern convolutional neural networks for image classification, combine multi-scale contextual information by consecutive pooling and subsampling layers that lower the resolution. However, semantic segmentation requires multi-scale contextual reasoning together with full resolution predictions, such as dense predictions. Several methods have therefore been proposed to tackle the opposing needs of multi-scale inference and full resolution output. Dilated convolutions enlarge receptive fields of neural networks with loss of resolution. The dilated convolutional operation corresponds to a regular convolution that skips pixels while applying the filter. This allows for efficient multi-scale reasoning without increasing the number of model parameters. At Deep Lab semantic image segmentation with deep convolutional nets, atroz convolution, and fully connected serifs extends this idea by using multiple dilated convolutions with different sampling rates in parallel. In contrast, at SegNet, a deep convolutional encoder-decoder architecture for image segmentation, an encoder-decoder network is proposed, which is with skip connections. Each decoder layer maps a low resolution feature map of an encoder max pooling layer to a higher resolution feature map. In particular, the decoder in their model takes advantage of the pooling indices computed in the max pooling step of the corresponding encoder to implement the upsampling process. This eliminates the need to learn to upsampling and those results in smaller number of parameters. Furthermore, sharper segmentation boundaries can be obtained using this approach. While activation maps at lower levels of CNN hierarchy lack information specific to object categories, they provide information of higher spatial resolution. Gaisi and Lewkes leveraged this assumption and proposed to construct a Laplacian pyramid based on a fully convolutional network. Aggregating information at multiple scales allows them successfully refine the boundaries reconstructed from lower resolution layers. They achieve this by using skip connections from higher resolution features maps and multiplicative confidence gating, penalizing noisy high-resolution outputs in regions where low-resolution predictions have high confidence. Deeper CNNs are also widely used. In the figure, comparison of deep convolutional neural networks as plain CNN networks, residual networks, and dense networks are as given. Before proceeding, it is also wise to state that in robotic applications such as autonomous driving, we usually have access to videos rather than single image frame. The temporal correlation between adjacent frames can be exploited to improve segmentation accuracy, efficiency, and robustness. The scene usually changes only slightly between two adjacent frames. Thus, given correspondence between two frames, semantic labels can be propagated in the time or corrected using temporal information. There are also such studies as label propagation, scene understanding. Let's continue with the metrics. The performance of methods for semantic segmentation is usually evaluated using the intersection over union method, which is defined as the number of true positive pixels divided by the sum over true positive, and false negative pixels. As classes with larger segments will have larger effects on the intersection over union score, one of popular dataset cityscapes also report the instance level intersection over union metric, which weights the contribution of each true positive and false negative pixel by the ratio of the average instance size of the respective class with respect to the respective ground truth instance size. These two metrics is used for two Plano trees, for classes and categories. Top 3 group based on the metrics for cityscapes dataset is given in the figure. Let's continue with the popular datasets. There exist many large-scale realistic datasets for semantic segmentation. The most popular datasets are Pascal-Vogue, Microsoft Coco, and Cityscapes. Recently, several companies also created new datasets which focuses on autonomous driving scenarios such as Mapillary, Apollo Space, and Berkeley Deep Drive. Also, it's wise to mention Audi's and Waymo's datasets. In addition, there exist several synthetic datasets for semantic segmentation like Cynthia and Playing4 datasets. Here in my project, I will be using city spaces as it's most relevant to the autonomous driving scenario. City spaces provides 5,000 images with high-quality dense annotations and 20,000 additional images with coarse labels obtained using a novel crowdsourcing platform. In contrast to 2D semantic segmentation, there are only a few datasets that address the 3D semantic segmentation problem. Furthermore, these datasets are either limited in size or in the number of classes. The city space datasets focuses on semantic understanding of urban street scenes. In the following, we give an overview on the design choices that were made to target the dataset's focus. Dataset features are as given in the slide. Let's continue with the state of the art on city spaces. In autonomous driving, as a challenging research topic, recognition of road, traffic sign, lights, vehicles, and pedestrians are types of perception problems. In traditional vision approaches, batch-based object detection where each of these items are to be found by different algorithms independently in modern-day approaches. Researchers have started to think those problems as a unified problem as being they are part of the same scene. The task of full image semantic segmentation aims to solve the problem as aforementionedly unified. A drawback of the solution, accuracy at the expense of high increase in network complexity, making them unfeasible in terms of computational resources. On the other side, some works have focused on efficiency by proposing architecture that can reach real-time segmentation, but this is normally at the expense of accuracy, in other words, aggressively reducing network parameters. In this project, I plan to work on this problem. I would like to work on an architecture that achieves top efficiency and accuracy without sitting on only one of these sites. I would like to work on a full image semantic segmentation project which is designed to maximize performance while keeping an efficiency that is suitable for real-time operations in modern GPUs. Due to time and other limitations, I will briefly talk about paper. The table shows the leaderboard of city space for pixel level semantic labeling task. All methods are trained on the dense dataset comprising 5000 densely annotated frames. Methods are additional trained on the coarse dataset with additional 20,000 frames are marked in the table as we discussed earlier. The state of the art in semantic segmentation shows very similar accuracy in terms of intersection over union and instance level intersection over union. Number 5. Extend the pyramid scene parsing network (PSPNet), which is number 12 with an advanced fusion mechanism. They propose gated full fusion modules which enable for very pixels to fuse only the relevant information from different feature maps. This allows better accuracy on fine level details than number 12. In contrast, number 1 presents a multimodal fusion approach that fuses features extracted from images and depth. The feature extraction method is based on the full pre-activation ResNet with multi-scale residual units as well as an efficient variant of astrospatial pyramid pooling given in number 10. Number 3 follows a different approach and introduces a relation module that correlates features with their spatial neighborhood by shifting the features in four directions: left, right, top, down, using predefined offsets while passing them through gated recurrent units. The features are extracted using a ResNet-like architectures in number 14, modified with dilated and deformable convolutions. Number 1 extends this idea by exploiting additional offsets to correlate features over larger neighborhoods. This allows them to outperform all other methods on city space table. Most existing network architectures for semantic segmentation are designed by the developer. Recently, a new line of work proposes to search for novel architecture in a properly defined search space. Number 2 addresses three dense prediction problems as street scene parsing, person part segmentation, and semantic image segmentation with an architecture search. In number 2, Xkapton's three famous paper as the backbone network and built recursive search space from three popular operators as one-to-one convolution, tree-to-tree atrus convolution, and average spatial pyramid pooling. Finally, they adapt random search algorithm to explore the recursive search space by evaluating 28K architectures on 370 GPUs. They find an architecture that achieves state-of-art performance on city spaces. But as I stated earlier, as being on X device applications, such networks are hard to assemble. Let's continue with the most popular studies. There are lots of studies on this area as semantic segmentation for autonomous driving and robots. They can be given as for scene understanding, deep multispectral semantic scene understanding of forested environments using multimodal facial. Human-robot collaboration for semantic labeling of the environment. Incremental dense semantics is stereo fusion for large-scale semantic scene reconstruction. Joint semantic segmentation and 3D reconstruction from monocular video. For general autonomous driving papers that is subjected as semantic segmentation paper, an honorable mention can be understanding high-level semantics by modeling traffic patterns. Let's continue with the recent studies. As of recent successful studies, the following list can be given as dense dual-path network for real-time semantic segmentation, DFA-net, deep feature aggregation for real-time semantic segmentation, SNet, edge-based semantic segmentation network for real-time semantic segmentation in traffic scenes, LetNet, lightweight encoder-decoder network for real-time semantic segmentation. Recent progress in semantic image segmentations. Survey papers also can be looked at the given index. And lastly, references. Thank you for your time, consideration, and efforts.